Hello and welcome. We're always told the simplest answer is a straight line. But what happens when the real world gets messy? What if you need to predict a simple yes or a no? Or model something that, well, curves? Today, we're going to dive into the awesome tools data scientists use when a straight line just doesn't cut it. Seriously, just think about it for a second. How does a company figure out if you're going to buy their product? Or how does a manager know if one of their best employees is about to quit? These are just basic yes or no questions, right? But predicting them, that takes a special kind of thinking. And to understand it, we first got to go back and really master the tool we all think we know, the straight line. So let's start with a model that seems, super straightforward, the good old straight line. But it turns out, for it to actually work the way it's supposed to, it's got some hidden rules. And believe me, a few really cool tricks up its sleeve. Okay, we all remember this from school, right? Linear regression. The whole goal is just to draw the single best-fitting straight line you can through a bunch of data points. It's a really powerful way to see how one thing, say how much you spend on ads, might affect something else, like your sales. But here is the catch, and it's a big one. For that line to be trustworthy, for its predictions to actually mean anything, it has to play by some very specific rules. You can think of them like the terms and conditions you have to agree to before you can use the software. First up, and this one might sound kind of obvious, the relationship you're looking at has to actually be a straight line. I mean, if your data points naturally form a beautiful curve, trying to force a straight line through them, it's not going to give you anything useful. And next up is a giant word, homoscedasticity. Don't worry about the name. It's a fancy way of saying that the errors, so the distance from each of your data points to the line, are spread out nice and evenly. If they start fanning out like a cone, that's a red flag. It means your model is getting less and less confident as the numbers get bigger. Not good. So a straight line is fantastic when you have numbers predicting other numbers. But what happens when what you really want to do is compare different groups? Like, how does satisfaction at work compare between people who've had an accident and people who haven't? That's not a number. This is where we get to our first really clever trick. It's called a dummy variable. And it's this brilliant little hack that lets us turn categories into numbers that our model can actually understand. So for example, we can just assign a 1 if an accident happened and a 0 if it didn't. Simple as that. And just like that, we can plug this new variable right back into our classic linear equation. So now, satisfaction equals some baseline number, beta 0, plus another number, beta 1, multiplied by our new accident at work variable. Let's break down what that actually does. Okay, so if an employee did not have an accident, their value for our dummy variable is 0, right? Well, anything times 0 is 0. So that whole second part of the equation just vanishes. And their predicted satisfaction is just our baseline, that beta 0. So then, what's that beta 1 all about? Well, that single number is the golden ticket. It represents the change, the difference in average satisfaction for the group that did have an accident. It perfectly isolates the impact a workplace accident has on morale. Pretty cool, huh? All right, so we've successfully used our straight line model to compare groups. But now it's time for the main event, the big question we started with. How in the world do we predict a simple yes or a no? Well, we definitely can't just use our trusty straight line for this one. And why not? Because the straight line can just keep going up or down forever. It could predict a probability of, say, 150% or negative 20%, which is just total nonsense, right? We need a model that's locked between 0 and 1. And the solution is this absolutely beautiful thing, the sigmoid, or S-shaped curve. This is the secret sauce behind logistic regression. Just look at it. It's perfectly stuck between 0 and 1. No matter how wild the inputs get, the output is always a valid probability. So, how do we get from our simple straight line to this amazing curve? It's actually a really clever three-step journey. We start with plain old probability, then we convert it to something called odds, and then, here's the magic, we take the logarithm of the odds. That final step, log odds, basically takes that squished 0 to 1 scale and stretches it out into an infinite line. And once we have a line, we can connect it right back to our linear model. And seeing how we interpret the results is where it all clicks. In a model that was predicting if employees would quit, the coefficient for their satisfaction level was negative 3.8. That negative sign, that's everything. It tells us that as an employee's satisfaction goes up, the log odds of them quitting goes down. Bottom line, happier employees are way less likely to leave. Okay, so far we've been really clever.
We've bent and twisted our linear model to do all these new things. But what happens when the real world just straight up isn't a straight line?
Yeah, sometimes relationships are just curvy. Think about diminishing returns, right? The very first dollar you spend on marketing has a huge impact, but the millionth dollar you spend barely moves the needle. For situations like that, we have other tools like polynomial regression for U-shaped curves or logarithmic models to capture that exact flattening effect.
Let's make this real with a case study predicting house prices in Bangalore. The big problem the data scientists faced was that the price data wasn't clean at all. It was super skewed. So what was the solution? Instead of trying to predict the price itself, they predicted the logarithm of the price. This one elegant move completely transformed the data, and it let the model capture the really complex, nonlinear patterns between a house's features and what it's actually worth.
Whew. Okay, we've covered a ton of ground, but when you boil it all down, it's really about having the right tool for the job. So let's put together a quick and easy toolkit so you know exactly when to use each model.
Okay, let's recap this super quick. You're going to use linear regression when you're predicting a continuous number. You're going to switch over to logistic regression when what you need is a yes or no answer. And you're going to pull out the nonlinear models when you know deep down the relationship you're studying is a curve, not a straight line. Each one has its own unique superpower.
See, once you understand these models, you can move beyond just looking at data and you can start asking it really sophisticated questions. So the question for you isn't just what's in your data, but what shapes does it take? Is it a straight line, a curve, or a choice between yes or no? The answers are sitting right there, just waiting for you to ask the right question.